Okay, so first case is to find out the magnetic moment. A steel rod has a magnetic moment capital M, and if it is bent into a semicircular arc, find its magnetic moment. That is our question. This is our rod of length L. The magnetic charges are plus M and minus M. So its magnetic moment would be small m multiplied by capital M. Now if we bend this rod into a semicircular arc, now let's say the radius of this semicircular arc is small r. So in that case we need to find its magnetic moment. So what we are going to do, first of all let's find out the value of this radius r. Okay, so we know that the perimeter of this semicircular arc is equal to pi into small r, right? And the original length where was L, right? Capital L. So here L by pi will be the radius of this new semicircular arc. Alright. Now
Yeah.
the new effective length would be this 2r, right? That is 2L divided by pi, because this will become a north pole and this will become a south pole, right? In the case of semicircular arc, right? So this 2r will be our new effective length. Am I right or wrong? So in this case,
Right.
the new magnetic moment would be simply the strength of the pole multiplied by the effective length, that is 2L by pi, right?
Hmm.
That is 2 by pi. And what was M multiplied by L? It was our initial magnetic moment. So our new magnetic moment becomes 2 by pi capital M. So if we bent this rod into a semicircular arc, its magnetic moment decreases, right? Because 2 by pi is what? It is less than 1, right?
Acha, yes.
Now what happens if we, the next question is to find out, or you can say case 2, where we need to find out the magnetic moment of this arrangement. There are two magnets and the structure is given this way. They are placed on top of each other
Hmm.
this way. Plus m minus m. This one is plus m minus. Okay, and the question is we need to find its magnetic moment of this arrangement. So what we can do in this case? It is similar to the situation. Remember we solved a question where two magnetic dipole was given. I mean this type of charge configuration was given, right? Plus q, there was minus 2q, right? And we needed to
Hmm.
find out the resultant magnetic moment, right?
Yeah.
Again, what was the direction of electric dipole moment? Minus 2 plus charge or what? Yes. So here P is in this direction, here P is in this direction. So resultant would be in
Hmm.
this direction, right? This
Yes.
will be the resultant electric dipole moment. So similarly, here in this case, so first magnetic moment is in upward direction, yes or no?
Hmm.
Minus m to m. Always remember the direction of magnetic moment. it is minus m to m, similar to electric dipole. Okay, similar to electric
Yeah.
dipole moment. Okay, and here it is in this direction, right? So vectorially they are making an angle 90 degree with each other, right? So this will be its new magnetic moment, right? And vectorially we know that how to find resultant if the angle between two vectors are 90 degree. It will be simply m square plus m square. So that gives us under root 2m. This is the answer. Understood?
Okay. Yes.
Now in magnetism, remember we had Coulomb's law and it was given as k q1 q2 divided by r square. So similarly in this magnetism we have Coulomb's law of magnetism. Okay, so what's the Coulomb's law of magnetism? We know that there are two magnetic charges plus m and minus m, right? And they
Hmm.
attract each other, yes or no?
Yes.
So here we know that the force will be directly proportional to the product of these magnetic charges and it will be inversely proportional to the distance between them, right? Now if you remove
Hmm.
this proportionality, we'll end up with a proportionality constant. In electrostatic it was k, here in this case it will be mu naught upon 4 pi, right?
Yeah.
This is the Coulomb's law of magnetism, very similar to electrostatic one, right?
Hmm.
So when this force will become attractive, when both the poles, I mean m1 and m2 are unlike poles, right? And if they are
Hmm.
like poles, they will repel each other. Now remember in electrostatic we found out the electric force due to a single charge, right?
Yes.
And it was given as force divided by charge, right?
Hmm.
So similarly, what's the magnetic field due to a monopole? Let's say we have this monopole of magnetic charge M. So this was the electric field due to the charge, right?
Hmm.
So what will be the magnetic field due to this monopole? It will be simply, at point B, magnetic field would be what? Magnetic force multiplied by magnetic charge, similar to this electrostatic field C, right?
Hmm. Okay. Yeah.
So it's very easy, right? This chapter is very easy. It's just the mirror image of electrostatics or first
Hmm.
chapter, right?
Yes.
Now, if you replace this force by the usual formula, we'll end up with mu naught upon 4 pi multiplied by m by r square. And here in electrostatics, it was kq divided by r square. So here also you can see the similarities. Mu naught upon 4 pi is constant. Here k is constant. Here magnetic charge. Here it is electrostatic charge. There is r square. There is I
And
square. Good.
okay. Yes.
Very good. Now let's find out magnetic field due to a bar magnet. So let's say this is our bar magnet, plus M minus M. This is its center, okay? Let's say the length of
Yeah.
this bar magnet is 2L. So that means this is length L, and we are interested to find out the magnetic field at this point P, okay? So we know
Yes.
due to this positive M, the magnetic field would be in this direction, and due to this negative M, magnetic field would be in this direction, right?
Yes.
So on this axial position, this is our axial position, right?
Hmm.
Magnetic field is given by mu naught upon 4 pi multiplied by 2m cross r divided by r square minus l square to the power whole square, okay? And for the shorter bar magnet, that means if L is greater than R, B axial or magnetic field at the axial point is given as mu naught upon 4 pi multiplied by 2m upon r cube. So remember we found out the electric dipole, electrostatic field due to dipole, and it was 2 kp upon r cube. Remember? Hello.
Yes, sir.
So it is similar to that. See, mu naught upon 4
Hmm.
pi is constant, k is constant. Here it is 2m.
Uh,
Here it is 2p, r cube, r cube. So you only need to remember one chapter's formula. You will automatically remember another chapter, right?
hmm.
So it is very useful. I'm not deriving this formula, okay? But you
Okay.
can derive it by looking this the derivation of this formula, okay? Electric field due to
Hmm.
electric dipole. It is similar to that. Just notations are different, okay?
Okay.
So same goes for the equatorial point, okay? Magnetic field on normal bisector or equatorial point. This is our magnetic dipole. We are interested to find out the magnetic field strength at point P. So it is given as B is equal to mu naught upon 4 pi multiplied by capital M divided by R square plus L square raised to 3 by 2. And if L is very greater than R, then magnetic field is given by mu naught upon 4 pi M by R, where R is this distance and 2L is the length of this magnet, okay? So again it is similar to the electric field due to electric dipole, right? And that was
Hmm.
Kp upon R. Understood?
Yes, sir.
So very important note, for shorter bar magnet, B axial, that means magnetic field at axial point is given as 2 multiplied by magnetic field at equatorial point or normal bisector. So very important formula. Once this question was asked in NEET exam, and it can be really useful while solving the problems of magnetostatics, okay?
Okay.